Alright, so basically, if you're taking physics or you took physics at some point, you probably should have seen this equation. Right, and this is one of the kinematic equations. Basically describes the position of an object over some time under constant acceleration. So today I'm just going to derive this equation. So let's see, if we have constant acceleration, we can say, we know that acceleration, right, is equal to dv by dt, right? And acceleration is constant, that's equal to some number a, where a is just, like, I don't know, 1, 2, 27, right? So we can solve this equation pretty easily. We can just say that, we can say dv is equal to a dt, and just integrate both sides, right? Then we can get that v is equal to at plus some constant. Now, before we go any further, we should probably figure out what this constant represents. So let's think about this. If we say that t is equal to 0, right, then no acceleration has happened. And suppose we have an object, right? It's going at some velocity and it's gonna accelerate over some time with constant acceleration to another velocity. When t is equal to 0, no acceleration has happened, and the object is still going at the velocity it was going at before any acceleration happened. So basically, it's just going at its initial velocity, right? Because when you have the object at its initial velocity, it's going to accelerate over some time to a final velocity before an acceleration. Before an acceleration, when t is equal to 0, velocity just is initial velocity. So we can say that c actually represents v0, v sub 0, initial velocity. Alright, so we solve for velocity as a function of time. One position. So we can use our second definition. We know what velocity is. It's a change in position over change in time. Change in position over change in time. dx by dt, that's equal to velocity. Right? And we know what velocity is. That's just at plus v0. This is equal to at plus v0. Right? So you know the drill. We can say that dx is equal to, dx is equal to at plus v0. Why did I say v0? v0, I should say v0, don't say v0. So v0, so dx is equal to at plus v0 times dt. Right? I know the drill, just integrate both sides. Right? And now basically I'm gonna do this integral real quick. I won't go into the actual integration technique, but from the integral, from integrating, you'll get that x, right, is gonna be equal to our position really. X is going to be equal to 1/2 at squared plus v0 t. So yes, I write that time. v0 t plus, not a constant. I should probably call it c1 and c2, really. We mathematical. But basically, right, plus another constant. Now, we have our position as a function of time. We need to figure out what this constant is. So let's see here. Let's think about this. We have an object at some position, right? It's going to accelerate over some time and reach a new position. So if we say that t is equal to 0, right? If t is equal to 0, these two terms drop out. So if t is equal to 0, then the object is still at its initial position, right? Before it accelerates to a new position, right? So that means c2 needs to be our initial position. So x-naught, right? Because you can think about it as just the object's position before any acceleration happened, right? So basically when t is 0. So that's basically it really. That's our kinematic equation right here. So that just leads to our kinematic equation we have right here. X is equal to 1/2 at squared plus v0 t plus x0. Do I need to write that down again? No. But that's for emphasis. But yeah, really, that's basically derivation, just a bunch of integration, really. So yeah, not too bad, and stay tuned for more cool stuff like this.